Thank you all for coming. In the next couple of minutes, I'm going to be telling you about this new way of probing quantum materials, in particular probing electronic correlations in these materials. We have been exploring this with the blue waters. Okay, so quantum materials are all about collective behavior. So we have 10 to the 23 electrons and ions interacting and moving around in the system with degrees of freedom like position and spin, and that turns out to very often result in complex behaviors. For instance, it's this collective behavior that determines whether electricity conducts along a material, like if electrons are stuck around the atoms, generating an insulator, or if they are metal, where electrons flow across the system. It also determines magnetic ordering, whether the material is non-magnetic or magnetic, whether this magnetism corresponds to little magnets in each atom, all aligning along the same direction, anti-aligning, or even not ordering. All these are common properties very frequently observed in many materials. But there are some other properties like high temperature superconductivity or unconventional magnetic orders that are just happening in a couple materials. And these are very interesting, and people think that they will be able to do very interesting devices with them. So we are really interested in looking for materials that show these unusual properties. And an interesting thing is that most of these materials, most of the materials that are known to show these properties, they seem to have a strong coupling between magnetic degrees of freedom and orbital degrees of freedom. So these little magnets and the electrons going around in the material interact strongly. Okay, take for instance the example of the iron-pnictides family. These materials are essentially layered. You have layers of iron atoms that are usually arranged in a square lattice, in a two-dimensional square lattice. And these irons, they have a magnetic moment, and naturally they tend to anti-align between each other, so as I represent here. The issue is that we also have some electrons flowing around in the system. And these electrons don't like to hop to atoms that have opposite alignment to the atom they are coming from, because that's energetically unfavorable. So in the end, they act as effectively transmitting or mediating an interaction between neighbors that makes them want to align with each other. So we have two kinds of interactions here in this kind of system. One that favors anti-alignment between neighbors, and another one that favors alignment. In the particular case of these materials, the ground state is going to be this kind of magnetic order that is not that common, where we have lines, stripes of up magnets and down magnets. This is an example of this coupling between magnetic degrees of freedom and charge degrees of freedom. We also have another situation in these materials. Most of these materials from this family are high temperature and conventional superconductors. And the community these days is more or less in agreement that the pairing between electrons in these kind of materials is mediated not by phonons, like in conventional superconductors, but instead by magnetic excitations between these electrons and the local magnetic moments. Okay, so we really want to find more materials that show this kind of physics, that show this kind of coupling. The question is there any way that is cheap to estimate this kind of coupling in a material? So we came up with a way that we think it's effective at estimating this coupling. So in this figure, I'm showing one element, barium, iron, arsenide in this iron-pnictide family. Here is the crystal structure, we have the iron atoms in this layer here. It's these red spheres. And these 4 panels are essentially top views of the crystal structure. And we are looking, essentially imaging the iron layer. On the top panel, we are looking at the charge density in this layer, and at the bottom at the spin density. The small points here are essentially the atoms. The colors are the same. The irons are really inside these spheres, these iso density, charge density spheres. The 2 columns stand for 2 different magnetic orders, where here we have the stripe order that I was just telling you about, that is the ground state in this particular system. And here we have an excited state order, that is this antiferromagnetic nil order. So the idea of this probe is to essentially excite, generate an excited state, an excited magnetic order. So this is the excited magnetic order, this is the ground state, and see how much charge rearranges in comparison to the ground state. So in order to do that, we just subtract the 2. So we subtract these 2 guys, and we have this kind of density surfaces. Red and blue stand for positive and negative. We do the same thing for the spin densities. And then we essentially construct a kind of a susceptibility, where we are essentially taking the ratio of these 2 and seeing, okay, we change the magnetic order from here to here. How does charge density rearranges in that case? So the mathematical way of doing that is essentially taking an integral of all this space, here, and the integral of the density, charge density there. We average over different magnetic orders, excited magnetic orders, to have a number that tells us about the strength of this coupling in a given material. The interesting thing, as I show here, is that different materials have very different responses. This guy is the one that I was just discussing. This other guy is a cuprate that is known to be a high temperature superconductor also. But you see that charge rearranges very differently in this case when compared to this one. And this is an insulating magnetic material that has a much weaker response. So qualitatively, these responses are different, but the magnitude can be kind of condensed in this charge spin susceptibility that I introduced in the previous slide. That is what we are going to be measuring in each material. The question is, can this coupling, can this charge spin susceptibility distinguish different materials, the ones that have this interesting kind of physics from the ones that have the usual kind of less interesting physics? In order to test that, we looked at a set of 35 materials. Some of them have interesting electronic phases, like these guys here that are superconducting and have strange metal behavior where electrons flow across the material in weird ways. They have non-trivial magnetic states. Most other guys have the typical kind of behavior, not they don't have these unusual phases. Okay, in order to compute this quantity, we essentially use density functional theory. We use the DFT plus U functional. That is a functional that assigns a larger interaction whenever 2 electrons are sitting on top of transition metal atoms. That should be like that because we know that electrons interact much more in transition metal atoms because these guys have open shell d orbitals. And the issue is that this U stands for the strength of this interaction, and we don't really know what's its value. So in the end, to control errors, we do several values of U to try to bond the errors from below and from above, from excessive U or defective U. Okay, we use blue waters to do high throughput calculations. For each material, we have to do several U's, several values of U's, several magnetic orders. This amounts to 80 to 100 calculations, DFT calculations, that take, in average, per material like 1,000 node hours. We have also been checking for a smaller set of materials if the results that we get with this methodology are accurate enough by using a quantum Monte Carlo method that is much more accurate but much more expensive, more than one order of magnitude. Okay, and here are my main results where I show the charge spin susceptibility for the materials in our test set. The interesting thing is that when we look at all the materials that are high temperature and conventional superconductors, they kind of cluster at medium to large values of this charge spin coupling. We also have a few, these two guys, for instance, that have the largest value. They are known to be disordered magnets and have also some strange metal properties. So they show some of these unusual phases. This guy here, it's a metallic ferromagnet that turns superconducting upon doping with H2O. It's not yet settled if this kind of superconductivity in this material is conventional or unconventional. And then this other material that has some phase transitions where conducting and magnetic properties change at the same time. So one other interesting thing is that all these guys with small values of this coupling are mostly conventional metals or insulators or magnets. So these results kind of point towards this probe providing us evidence that a medium to large charge spin susceptibility is in general associated with materials that show these unusual correlated phases. This might eventually accelerate the discovery of new materials that show these properties, like unconventional superconductivity. We have been working on that. And we are currently looking at a different set of materials that I've not shown here, materials that are very scarcely studied. And this charge spin susceptibility has highlighted a few of them that a group in UIC is now starting to look at and synthesizing these materials and exploring their properties to see if they have any of these interesting physics. Okay, here is my summary. Thank you very much.